Okay, we're here. Thursday, April 23rd. So we are on lab 12 today. So I'm going to go ahead and work through lab 12. We've written most of this code twice already, and some of it once. But anyway, I'm going to re-implement everything from scratch and just describe as I'm writing the code what it is that I'm doing. My hope is that in doing that, you just sort of get a reminder of the things to think about when you're working on the third project. Doesn't seem to be a whole lot of us here, so maybe just one of us. So you can own the show if you want to. Anyway, I'm going to do lab 12, and then I'm going to implement another function to try to help you with the third project. The second project scores have gone out, so if you submitted a second project, you should have gotten something back with the score in it. If you didn't get anything back, then we didn't get your project. So, or somebody misplaced it with me in the grader. So anyway, if you do not have a project 2 score in your inbox, please let me know, because if you submitted a project 2. Which most people did. Okay, so lab 12. Lab 12 is taking lab 11 and turning it into a template. So the main difference here is that it's a .hpp file, so everything goes in here. The entire implementation goes in here. The reason why we're doing that is because templates are a funny creature in C++, and compiling a template can be tricky, but you can eliminate the trickiness of compiling a template if you just do everything in a .hpp file. So the first thing I'm going to do, because I noticed this the other day when we were talking about it, is I'm going to update the node, because that's actually where the template is most important, because the template alters the data in the node. So just like before, a node for a singly linked list has a neighbor, and then it has a piece of data. And in the prior lab, we said we called it value and we made it an integer. But the whole point of making this a template is that we want to be able to store anything in our node. Anything. Any kind of value. Strings as values, ints as values, anything. And that's what templates allow us to do. So if you look up here at the top of the class, it is preceded by a template declaration. What this gives me is access to this T, which represents an unknown or generic data type, is how I like to describe it, which is how some other languages describe it. So T, I should be thinking in terms of a node stores data of type T, which is an unknown type, which it shouldn't matter, because what's in a node ultimately the list doesn't care about. It manages nodes, so it will create nodes, populate them with data, but the kind of data that it is, the node doesn't care. So T. So my node down here, no longer an integer, but a templated type T. And then I'm supposed to make a constructor. So that nodes can be quickly and conveniently created. So again, when I create a node, I'm going to be given some value that's of some type T, and I'm going to take it and I'm going to store it as the value of this node. And then I'm also going to make sure that I null out the next pointer, so that that link is in a known state to start. So there's the node complete. The singly linked list here doesn't really change. It still has a head pointer. And now we're just going to go back up to the top and work our way down. Okay, so constructor for the list. Now I'm not doing node anymore, I'm doing list. So now I'm thinking of the manager of nodes, not the nodes themselves. But it tells me what to do. It says take the head pointer and null it out. That's from this comment right here. And take the size, make it 0, because that's what the state of the list will be to start. The destructor is just going to use a helper function. So I might say this clear just to be consistent. But I'm going to use the list's own clearing function to manage the problem of cleaning up the nodes. But you've all seen this, so this is just repeating the same thing that we've seen for 2 weeks now. I'm just writing the code just to remind you what I'm thinking about as I'm writing it. Pushing on to the front. So the main thing here is that I try to be careful of I usually draw a picture, and then I try to be careful to not leave anything dangling anywhere. Move my camera's in a funny spot. Do I have my camera up yet? I do. Okay. So push front. Usually what I do is I just imagine that I have two situations that I might encounter. A situation where I don't yet have anything in my singly linked list, and a situation where I have at least one thing. And I need to make this function work for both situations. And then like I did with the doubly linked list, once I implement, then I go back and I test each situation again in turn just to make sure that it still works. So push front. The first problem is to make a node, which I'll just call n dynamically. So the node's own constructor is going to take that value and store it inside the node and also null out the pointer. So I have this thing. With n pointing to it. Make sure that you can see, you can. All right, so here's my new node, n. Then the trick is to always connect the new thing up before you mess with the old thing. So the new thing is the n, and I can see that because there's literally the word new here. N is the new thing. So to put n at the front of the list, I'm going to say, well, its neighbor should be the head of the list. So for example, in the second list, if I had an n down here, then I'm saying n's next, here's n, n's next is the same thing that head is, which is what I wanted. I want to push this on the front, make this one the new front one. Then I just, if I look at the other situation, by the way, if I say n's next is null, that's fine, because if n's by itself, and I say its next is the same thing as head, and head is null, well, that's fine. Then I move head. So I want n to be the new head, so I take head, and I point it to the same place where n points to. That seems right. N's next is null. I used to be empty. Now head points to n. N's next has nobody, so and then n eventually just fades away, but head stays in place, so that's good. And then on this one, same thing. So I take this head and I move it to the same place where n is, and then n fades away, left with head, and that's exactly what I wanted. So it works in both situations. Then I increase the size by 1. Okay, that's fairly easy. Pop front. So this one already tells me, be careful, you can't pop the front on an empty list. So I like to use my own functions when I can. So if this list is empty, I will throw the exception that it tells me to throw. Otherwise, what I want to do is remove the head node. So I'm going to do the same thing. I just handled this situation. Nothing to pop, so I throw an exception. But now I need to handle this situation. Where there's, I'm just sort of saying one or more. So I already handled none, now one or more. So in this situation, it's usually best if you're going to remove something to get an external reference to it. So I'll call this temp. So how do I make temp point to the same place as head? So I'm going to say node star temp is the same thing as the list's head, which achieves this standard. Oh yes, good catch. Yes, STD. Yes, standard. Thank you. Good catch. Okay. Thank you for the catch, because that would have been irritating to hunt that down later. Okay, so now I'm in this situation. I have temp points at the same place that head points at. To pop the front, I need to move head over. So I get a temporary pointer, and then I'll say that I'm going to take head and move it. This head equals move head to point at the next one over from the head. So it looks kind of funny because it's sort of two steps, but that's how it works. So I take head and I will move it to point at where head next is. So that moves it over here. Temp I still have, so I can still target this node, and this popping it means to delete it. So I'm going to delete that one, which removes the node from memory, and then I'll adjust the size down by 1. Pop front. And again, the reason I'm walking through this, this is the second time for this one maybe, is to kind of show you my process, how I draw the picture and consider different situations and adjust the picture and see if things still work. They don't always. Sometimes you mess up the picture, but the more practice you get, the less you mess up the picture. Okay, so remove the head node, did that. Return the value in the head node. So this one has the same problem if this list is empty. I can't. I'm going to be more careful about my copy this time. If the list is empty, there is no head node to get a value from. So I'll throw an exception. Otherwise, I'll simply return, I'll go to the head node and I will grab its value and return that. So the head node's value. Okay, size. So the size is just the counter, the size of this thing. To check if empty, I'll just compare the size against 0. It'll return true if the size is 0 and false if it's not. So true, it's empty, or false, it's not. That one's easy. Clear. I often in my own mind call this pass the buck programming, but the idea is if I already have functions that do at least a part of the job and I can figure out how to leverage those into more of the job, I'm going to do that. So if you think about it, clearing a list is simply a matter of popping nodes until the list is empty. And isn't it nice that I have a pop front? So all I have to do is say, as long as I am not empty, I'll pop nodes off the front. So it'll just keep cycling. until there's no nodes list. If it also tells me just to be careful about this. So if I clear a list, the head should be null and the size should be 0. And why not just be certain that that's going to be the case? In theory, by the way, this was going to happen anyway. But the documentation tells me to just be thorough and handle it, so I did. But in theory, if you look at pop front and the way it works, that should happen anyway. Okay, there's that one. Now, we've written all these before, and again, I'm just sort of talking through them to get you in this headspace a little bit, all these pointers. To string. What do I have in the includes? I have O string stream. All right, so I'll do an output string stream. I'll just call it output. So I'm going to build up that string stream with stuff and then return the string form of it. Okay, so iterating a list like this, it's wise in my opinion anyway. To not use any of the list's own pointers, because you don't want to accidentally move stuff. So what I'm doing here is I'm setting up two lists. I'm always sort of thinking, what would happen if it's empty? I need to be careful about that. And check, and of course the unit test will help, but I should be sort of checking to see if my algorithm would break on one of these situations. I look stuck. Well, I'm watching my own stream and I noticed that okay, I'm back to life. Okay, so how do we do this? Just like we did when we were popping nodes, I'm going to get myself a temporary pointer. Looks like I'm dropping a few frames, sorry about that. Hold on, let me refresh and see if your experience is terrible like mine. I hope not. Okay, so we've done this before, but it's safer to give yourself an external pointer. So I'm going to start out by just making a pointer pointed at this list's head. And then since I need to print all of the nodes, I'm going to use a loop to do that. So while temp is not fallen off, I'm going to do stuff. So I'm going to output. So I'm going to take temp's value and tack on a comma. And then I'm going to move temp to the next one over. So I can very quickly check, by the way, and tell that on this empty list up here, if I make temp point at the same place that head points to, that the while loop is immediately going to fail, because it's going to say while temp is not null, and on an empty list it's going to say, oh, it's null. I guess there's nothing to do. In this other case, what it's going to do is it's going to print the value and then move temp, and print the value and move temp, and print the value and move temp. I'm going to not do this same because I don't feel like delaying us on this too much, but I'm going to get a value, and then I'm going to, like we did before, I'm only going to print I'm only going to print the comma for temps who have a neighbor. So I'll walk this real quick. I'll just number these as 10, 20, and 30. Okay, so if I start here, then my loop is going to say, well, temp is not null, check. Output 10. And then if temp next is not null, I'll put a comma. And then move temp to temp next. Output temp's value. If temp next is not null, put a comma. move temp to the next one over, output a value. If temp next is not null, oops, it's null, so we don't do the comma, and then we move temp over. And then the while loop says, oh, temp is now null, guess we're done. So that's that whole algorithm. Hold on, I did something terrible with my editor. Okay, so we've seen that algorithm. Before, it's the same one. I just wrote it again to walk you through it again. Now we're going to go compile and see if the thing runs. So I've got to hide my projector for a second. I'll show you that I've got the lab files here. So I have the catch, I have the unit test file, I have the HPP file, and the thing that I'll just keep saying, and hopefully I'll get you out if you accidentally do it. Hopefully eventually I'll break you of the habit. I only compile the CPP files. Only the CPP files. And in this case, there's only one. So how does slist.hpp even get in there? Well, if we look at lab12.cpp, there's an include for it. And that's how HPPs get in there, is with includes, not with compiling. So do not compile HPP files. Notice, by the way, catch gets in there the same way, with an include, not by compiling. I am going to specify the output executable to be lab12.exe, and then we do the catch wait. I expect to pass this on the first go because we've written these same algorithms 3 weeks in a row. Okay, so everybody passes. That's what I would have expected because I'm just rehashing old code at this point, basically. So that's lab 12. You already had all that code, by the way, for the singly linked list. If you're worried about rewriting it, you don't have to. Lab 11 has all the same code. It's just a matter of where do you put it to turn it into a template. So that's all this is about, is can I turn it into a template and still have it work? So that's what we just did. But the underlying algorithms, they don't change. Okay, so it's roughly 25 minutes. So now we're gonna, I need to open it. Do I still have it? The doubly linked list. So the rest of this class today is me trying to give you a little bit more on the doubly linked list, and then we have 2 meetings next week where we can focus on where you're struggling. But I'll tell you my plan. I might even start the insert today and give you some hints about that. So I'm going to do pop back. And the reason I'm doing pop back is because I want you to take that and work on pop front for yourself. It's going to be very similar to the singly linked list, but you have to be careful because there's an extra pointer in the mix. So anyway, I did push front. And what my hope is that you will use push front to help guide you in making a push back. But you have to pay attention. And I recommend pictures to the pointers because you have a head and a tail now. So this is a doubly linked list, which means that the nodes have a next and a previous, and the doubly linked list keeps 2 markers, a head and a tail. Okay, so I gave you push front in the hopes that that would help you do push back. Now I'm going to sort of go to the other end and do pop back in the hopes that that will help you do pop front on a doubly linked list. then we're going to kind of model this on the pop back. Then you did something wrong. I don't know what to tell you. um, I passed, so you did something wrong. It's the same to string function. Just go copy it so we can work on this new stuff. It's the same to string function from lab 11 and lab 10. The same one. Didn't change at all. Right, so pop back on a doubly linked list. We're going to model this on the pop front on the singly linked list. We just have to remember that we got to pay attention to the pointers. Let me bring my camera back up because I'm going to draw this in a second. Pop back. But I remember with pop front in my singly linked list, and I'll even go show you, it's sitting right here. It had this exception throwing stuff. So I'm gonna take the same idea and I'm gonna do it again. So if this empty, if the doubly linked list is empty, then I'm going to do the same thing. Throw, I think it was a logic error. I'm just going to do the same empty list. Why not? Same thing. That, by the way, means that I should probably add to my list of goodies here. Add a get size and an is empty function, just like I had for the singly linked list. Okay, pop back. But now we got to be careful. So we already handled this situation. Where the list is empty. So now pop back. Can be a little intimidating because there's actually, with the doubly linked list, sometimes there's more situations to consider. So it's possible. So I have an empty list, a list with one node, and then a list with more than one node. And we need to be careful to make sure that our algorithm would work for any of these situations. So we're going to sort of test our algorithm across these. This we already handled, so that's good to go. List is empty, we don't do anything. But popping the back. So remember, pop back means from the tail end, not the head end. So I'm just going to start by what seems obvious to me, and then I will make adjustments as I sort of go back through and test out the idea. So one thing that I know is the simplest part is I simply need to grab a temporary pointer to the tail so that I can use that to delete the thing. And then I need to move the tail over. And in fact, it might be a little more obvious to you if we start with this one. So I'm going to grab a temp pointer to tail. I'm going to move the tail forward one. So I need to move the tail here. And to do that, I'm going to go not next, but previous. Toward the front. So I've already done that here. There's temp still sitting on the target. Tail had to move forward one. And then I'm going to delete this. Which gets rid of this thing. But there's a problem here. Because this pointer right here still thinks it has a neighbor. And it doesn't anymore. I just deleted it. So we actually need to clean that pointer up because it believes that there's somebody still there as a neighbor, even though there isn't. So now that's tails next needs to be nulled out. And then I'll reduce the size. By 1. So that's a lot more complicated because it's very easy to overlook a pointer. So all of the pointers related to the node that I deleted, they get cleaned up for free. But that pointer coming off tail, that's a problem. Okay, so now I'm going to go back a step and I'm going to apply it to this one and see what happens. So I'm going to make a temp, also pointing at tail. I'm going to move tail to tail's previous, which moves tail over here. And then you may notice that I have a weirdness going on here. Because head still thinks that's a good node, but my algorithm deletes it. And its links. So now you have head here who thinks, well, there's a node here, but I just deleted temp. Like everything about temp is now gone and head still thinks there's a node. So I need to write code to recognize this somewhat unique situation where, well, how can head be pointing at something if tail's not pointing at something? It's not possible. If moving head over points it at nothing, well, that means that probably head should be pointing at nothing as well. So I'm going to check for that. So right here. So if moving tail over made it null, then head also needs to be null. And that's the situation here. When we move tail over one, it became null. So if it becomes null, then I'm going to take head and also point it to null. Now they seem like they're out of order, but they're just both pointing at null. I just didn't feel like scratching the drawing up anymore. Okay, so now we keep going. We delete temp. Now we say this tail next, except for tail doesn't point at anything, for there to be a this tail next. So I got to protect that. So if this tail is not equal to null, then I got to do something. Before I knock down the size. So I'm going to redraw that just to walk through the algorithm again, but you can see that you got to think. You got to think a lot with a doubling like this. It's quite a bit more difficult. So let's draw the situation again. The freebie, I'm just going to use H and T to clean these up. Null pointer, so that throws an exception, that's fine. Okay, so now let's try it on the onesie. Okay, so in this situation, how does it work? So I'm going to grab a temp. And then I'm going to move tail to tail's previous. So tail, these both point to null. Hopefully you knew that. I'm going to move tail to tail's previous, so tail's sitting here now. Because moving tail to tail's previous takes it into null. And then I say if tail is now null, then head should also be null. So that seems okay. And then I say delete temp. So that takes care of this node and its links. And then I say if this tail is not null, oops, nothing to do here, and then I reduce the size by 1. Okay, so that seemed to work out for that situation. Now I'm going to put this situation back. And see if it still works on this one. So not empty. So temp is tail. Tail moves to the previous, up toward the front by 1. So tail moves up here. Seems okay so far. If tail is now null, which it's not, so we don't do anything. Now we delete temp. So that takes care of the node and its links. Still have this one sitting here that thinks that there's someone there. If this tail is not null, it's not, then this tail next becomes null. That's what we would want because there is no neighbor anymore, and then we'd reduce the size by 1. So that one's more painful to do than a singly linked list. But that's the process on pop back. So my hope is that you can use that to get yourself into pushback. It's not as easy as it looks, by the way. Don't wait till the last second. You're going to think that you're just all clever and you're going to change all the tails to heads and all the heads to tails, and it's going to crash and not work. So leave yourself time to deal with that. I know from experience, my own, and watching lots of students over the years, that we all think that we'll just swap out tails for heads and heads for tails and it'll work at the other end. And theoretically it would, but none of us ever seems to get it quite right, so we have to leave ourselves time to fix bugs. Okay, so now I'm going to give you, I'm going to start on insert. Which I hope gives you a hint about remove. You have to think about it, but it's there's some things that we can use for both. So insert, I think we just add data in, right? So void insert. We're going to be inserting a value. So this is instead of push front or push back, it allows us to insert values and keep them sorted. I need to be careful here because this is not an integer, it's not a string, it's not a bool, it's a t. Because t is the templated type that the nodes in my list hold. So anything having to do with working with values, getting a value will be this way. The back will be a t, the front will be a t. Be careful that you're not hard coding down to something like an integer or a bool or a float or whatever. It's a t. So I need to insert a t. But this will just be, I'll give you a starter on this and let you mull it over. So when we did clear, we're going to need to clear here as well, by the way. When we did clear in the singly linked list, I talked about using the functions that I already have at hand. So what I want to do for insert, so here's the idea. Let me draw a picture of it and show you the idea. So what insert is supposed to do, if you push front and push back, if you do push front and push back. So if I say push front, well, I don't need to draw the words. Push front and push back just sort of tack things on at the front and the back. So I can get sort of just all kinds of crazy randomness with that. If I'm pushing front and pushing back, they won't stay in order. And that's okay. There's applications of that, which I'll talk about probably next week now when we come back to this insert. But as a first introduction to the idea, if I'm pushing front or pushing back, the values inside aren't necessarily in any kind of order. They're only sort of in order in terms of when they arrived and on which end I placed them. Push front, push front, push front, push back. So they can be all jumbled up on the inside in no particular order. But if I use insert, then what I want insert to be intelligent enough to take values as they arrive and keep them in order. So this is what I would like to see as a result if I was using insert. This is a point of confusion for people, by the way. If you use insert, then you should only use insert. Because as soon as I push front or push back on a list that's all neat and pretty like this, it breaks. So you just have to keep it in your head that I'm developing this insert function, and I'm assuming that if someone uses insert, then they will always use insert. I develop push front and push back because I'm assuming if they use push front or push back, they're always going to use push front or push back, and they're not going to mix the two. There's not going to be a mixing of inserting and pushing front or inserting and pushing back. It's going to be insert, 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 or push front, push back, push front, push back, push front, push front, push front. They're not going to get mixed. So I'm actually writing functions that allow people to either do front back stuff or separately to do insert stuff. The functions are both in the doubly linked list, but I expect that no one's going to mix them together because it wouldn't work. So I'm writing this insert function to make this happen. But that doesn't mean that I can't use push front and push back when it makes sense to do so. So for example, if they are trying to insert a value and my list is empty, then it doesn't matter if I push front because it's the first one anyway. That doesn't matter. Hopefully that makes sense. So I'm not even going to develop an algorithm for that. I'm just going to use another function. If the list is currently empty, well, it doesn't matter. I can push it on the back too. But why do work? Just let push front work it out, do the work for me. Another possibility is that value coming in comes before or is equivalent to the value at the head. So imagine, for example, I'll do another picture. Here's my list to start, and they say insert 50. Well, there's no magic here. I'll just push front. So indirectly, I'm just going to push front. Now, if they do an insert 25, well, logically, I can tell that that's supposed to go here. Which is on the front, which is terrific because I have a function that already does that. So I don't need to reinvent the wheel. If I discover that the thing goes on the front, then I just use push front to put it there. Now I could have written this as a or kind of situation. But anyway, if the list is empty, just push it on the front. If the value I'm trying to insert on the list should come in front of the head, well, push front already does that, so I'll use it. Which hopefully then you can anticipate another situation, which is if the value comes after the tail. If the value comes after the tail, well, push back should handle that problem. I'll use other functions to deal with it. So there's really only one thing that causes me trouble, that makes this difficult, which is this last situation, and there's only one thing it can be, which is something in between two things. Something in between two things is hard. I guess maybe I'll go ahead and start working on it a little bit. This is a lot of code to take in one day. Probably I'm not. I'm going to stop there and just leave myself a note that this is we're going to pick up. So what I'm encouraging you to do is be an engineer here. Don't reinvent the wheel. If you have something that solves a part of your problem, use it. The other thing is to improve or enhance or just continue mastering the skill of adapting something to different situations. And what I mean by that is push front gives you everything that you need to think about to do push back. You just have to be careful because you're working at the tail end instead of the head end. But if you're given how to push front, you should be able to adapt that into push back. I did the same thing with pop back. So that's working from the tail end, but in theory, you should be able to adapt that to pop front. It's different than singly linked list, but it gives you everything that you need to consider to pop the front. Inserting may not seem like it at the moment, but inserting and getting and removing, these three functions, get, insert, and remove, you can do this trick with all three of them. If the thing you want to get is on the front, then use front. If the thing you want to get is on the back, then use back. Otherwise, you have to look for something in between things. Same for remove. If the thing you want to remove is on the front, pop front. If the thing you want to move is on the back, pop back. Otherwise, you have to look for something in between two things. So those three are very, very similar up to a point. Let's see, clear. You can use the same algorithm as you did with the singly linked list. You just have to remember that when you've done deleting the nodes that you have to null out the head pointer and the tail pointer and set the count to 0. Get size doesn't change. Whether or not it's empty doesn't change. To string doesn't change. So that's fortunate because these things don't really care if it's a doubly linked list or not. But most of the rest of them do. The destructor, that's pretty easy. You just call clear to help. Okay, so I'm going to save that and I'll keep coming back to that. So hopefully you will take my encouragement to see if you can, I got work to do here. Which you can do for yourself as well. Get yourself up to the point where you're like, okay, now I got to figure out the hard part. Okay, pardon. I am done. I think that's plenty enough to try to smash into our brains in one day. So I'll sit here for a couple minutes and see if I get any questions. won't that thing center me? Who knows? Oh, I know why. That doesn't matter. Oh, I know why. It's because of my teeth. Somewhat. Thanks for being here. Appreciate it. Hopefully there's something of use in there. Remember the project will be due, well, now it's extended to a Sunday, so it'll be Sunday something. Early May at this point, like Sunday, May 3rd or something like that. So next week is our last opportunities, Tuesday, Wednesday morning, and Thursday to ask questions about that. So try to get yourself in a position where you can ask questions if you need to ask questions.